In this video, we're going to learn the Doppler effect and its implications when an object that's making a sound moves and what frequency we hear while it's moving. The Doppler effect is the change in frequency of the sound detected by an observer. Here's an example of a situation where a fire truck's making noise and it's not moving. The truck is at rest and the observers are at rest. What do the observers hear? So pause the video, think about what the observers hear. The answer is they hear the actual frequency of the truck. And you'll notice that these are the condensations. In other words, you can think of these as the crests. These are the compression areas of the sound wave. And from compression to compression is a wavelength. You can see how the wavelengths are not changed at all on either side of this truck, so they hear the actual frequency that this truck is making. Here we have an example of the truck is moving and the observers are at rest. What do the observers hear? So pause the video and think about what happens to the frequency that the observers hear while the truck is moving either towards them or away from them. The answer is the observer on the left hears a lower frequency and the observer on the right hears a higher frequency. The waves here, you can see that the crest, the compression areas are much closer together, so this wave will pass by this person's ear more frequently, and since these waves are now farther apart, they're larger wavelengths, the waves will pass by this person less frequently. So you have a higher frequency on the right, lower frequency on the left. Here we have a Doppler effect animation. There's this green dot in the middle that's making a sound, and we can't hear that sound, but we could see the sound being made. And this object is not moving yet, but as soon as we start to get to move, you can see that the waves will crunch in. So here we have it moving to the right, and you can see it's a higher frequency on the right now, it bounces off. On the left-hand side, you'll see the higher frequency on the left and the lower frequency on the right, smaller wavelengths on the left, larger wavelengths on the right. And so here's a nice little representation of what the Doppler effect, an example of the Doppler effect is. Now, if this object goes faster, you see that those waves get even crunched in more. So I'm having to go faster. And now we can start seeing what a sonic boom will do if you go Mach 1. If you go the speed of sound, you'll see that bright red spot. Now all those sound waves are all together, and all those sound waves now are at one spot. And those sound waves, that's the big noise you hear, is that booming noise is when all the sound waves are all together the same spot. This object here is moving at the speed of sound, so all the noise is all at one spot. Here's what happens if you go faster than the speed of sound. The sound waves are trailed behind, so there's not a sonic boom in this case because all the sound waves are behind it, not built up at one spot. Now we want to learn how do we calculate this observed frequency. Not the, sometimes we'll be calculating actual frequency, but what typically happens is you have to find out how to calculate the observed frequency of this sound, what you're hearing. And here's our equation. It's F sub O is the observed frequency. F sub S is the frequency of the source. So F sub S is the actual frequency of the sound emitted by a source. The V is the speed of sound. That just plain V that you see over underneath on the right hand side, that's just speed of sound. And air can be typically 343 meters per second, but it changes as temperature changes. V sub S is the speed of the source of the sound. So if there's a fire truck or an ambulance making the sound, that's the speed of the fire truck or ambulance. V sub O is the velocity of the observer. We need to know is the observer moving or not. Okay. And F sub O is the frequency the observer hears. That's over here on the left. So you're going to want to pause this video, write these equations, make sure this equation's in your notes and this information's in your notes. We also want to make sure we know when to use the plus or minus sign in the equation because it is plus or minus in the numerator and the denominator of that Doppler effect equation. You have to think about what the action that is occurring is causing. So if you're moving towards the sound, it's going to be a higher frequency. Away from the sound, it's a lower frequency. So you have to realize whether it's plus or minus on top or bottom, whether the number is supposed to be bigger or larger. If a lower frequency should occur, you have to make the number on top of the fraction lower or the number on the bottom higher. So you have to use plus or minus to make that happen. So let's try some examples here. Read through the example 10 and try it, and then we'll go to the answer, see if you get it correct. It says a high-speed train is traveling at a speed of 44.7 meters per second when the engineer sounds the 415 hertz warning horn. The speed of sound is 343 meters per second. What are the frequency and wavelength of the sound as perceived by a person standing at a crossing when the train is approaching and leaving the crossing? So go ahead, pause the video, try that on a separate sheet of paper, and see if you get these answers correct. And we'll have the solution to example 10 here. Our equation breaks down to this right here, because on top over here we had velocity of the observer is 0, so this whole piece right here went away. We're using the minus sign below because we need to make the number higher because the train is coming towards us. So we have to make the observed frequency higher, and you do that by making the number in the denominator lower. So you do a subtraction here. Plug in your values and you get 477 hertz. If you want to solve for wavelength, you use the velocity equals frequency times wavelength and come up with 0.719 meters. Now if you do this for going away, you would do the exact same equation up above, except you would use a plus sign right here. And you would end up with, if you did that, if you'd put a plus sign right here and the plus sign right there, your answer would have been 367 hertz instead of your 477. And then you put it into your wavelength equation here, and you would have ended up with 0.935 meters. So the only difference between this first two and this last one is this 367 hertz that you get by having a plus sign instead of a minus sign right here. Because it's moving away, we have to have a lower frequency. Here's another example that is a slightly different approach to this problem that you'll see sometimes. It says two trucks travel at the same speed. They are far apart on adjacent lanes and thus approach each other with essentially head-on. One driver hears the horn of the other truck at a frequency that is 1.2 times the frequency he hears when the trucks are stationary. So this observed frequency is 1.2 times larger than the actual frequency. The speed of the sound is 343 meters per second. At what speed is each truck moving? So what I'd like to do is see if you can, pause the video, see if you can figure out how to approach this problem, and then we'll have the solution in the next slide. You'll notice in this equation, instead of having the Fs right over here in front on the right-hand side of the equal sign, we've divided it over, so we have FO over Fs. And we know that FO over Fs is 1.2. We know that ratio. You know the observed frequency is 1.2 times larger than the frequency of the source. So we also know that they're coming towards each other, so that the observed frequency is going to be higher. And so it's going to be plus on the top, minus underneath. All right, the observer is moving towards the source. That's why you have a plus here. The source is moving towards the observer. That's why you have a minus here. So you go ahead and you get a common denominator. You go through the mathematics of all this. You have to add these two fractions on top together, these two fractions on the bottom together. So what you do is you get a common denominator, add them together, then you do some algebra, and you end up with V plus VO all over V minus VS equals 1.2. The observer and the source are moving, and if you solve this right here, because you plug in 343 meters per second for V, and VO and VS are the same number. You just put X in there for that. So you go ahead and you end up with an answer of 31 meters per second moving towards each other.